We're back. Chapter 1, Section 1.2. Now we're going to talk about linear equations and rational equations. So I promised we'd come back to graphs of lines, and here we are. It didn't take long. Here we are. And also rational equations. We saw x and y axes and the rectangular coordinate system and how if you're given an equation to figure out what the graph looks like by just plotting random points. And we saw x-intercepts, y-intercepts in the previous section. So we'll get a little more detailed into specific types of graphs this time in this section. What is a linear equation? A linear equation is in one variable x is an equation that can be written in the form ax plus b equals 0, where a and b are real numbers and a does not equal 0. So just kind of something you can solve for x without having to factor or any weird stuff. Just solve, something here, solve for x. I can move the one term over and divide by something or something like that, and it would be all good. Easy peasy. This is how we would go about generating equivalent equations. Okay. An equation can be transformed into an equivalent equation by one or more of the following operations. First, you can simplify an expression by removing grouping symbols and combining like terms. So maybe I'll make one up so we can follow along as we go. Let's see if I want to. Let's see if I have. No, maybe not that. 4 subtract 2x plus 3 equals 0 or something. There we go. We'll try to solve that. So the first step would be, as they said, try to simplify an expression by removing any grouping symbols and combining like terms. So I think they mean the parentheses here are here. That's grouping the 2x and the 3, but I can distribute that negative sign or minus sign and it would be equivalent. So I'll rewrite it as 4 subtract 2x, and then the minus sign or the subtraction sign should go to the 3 as well. So I've kind of done what they said at first, simplify an expression. I removed the grouping symbols, but now I should still combine like terms. So this whole part, I'm still kind of doing step 1 here. There are some like terms on the left side of the equation. 4 take away 3 is 1. Then I have that minus 2x that doesn't have a like term to combine with. So that's what they mean by, remove grouping symbols, combine like terms, if necessary. Sometimes you can't do that. There's no way to do that. But sometimes there is. Second step, add or subtract the same real number or variable expression on both sides of the equation. As we've kind of seen, I feel like we've done this in the review. But what you want to do is now get rid of anything that's adding or subtracting next to x. Not the coefficient of x yet. We're going to get rid of this thing that's on the same side of the equation as x. Whatever sign it has, in this case it's positive, I'll do the opposite and subtract it from both sides. That way 1 and -1 add up to 0 and it disappears. So I'll just be left with the -2x on the left side, and now 0 and -1 make -1 on the right side. We've done that. Okay, now the next step would be multiply or divide by the same non-zero quantity on both sides of the equation. And then it kind of sound like it's left open, but what we want to do is get rid of this coefficient in front of x. So, and since it's multiplying by x, technically, -2 times x, I could divide both sides by it. There we go. So x is now by himself because -2 divided by -2. Technically, I could put a 1 here, but you don't have to. -2 divided by -2 is 1x. And then I've got a negative divided by a negative is a positive, but I'm just going to leave it as 1/2. So x must be 1/2, yeah. And then the last step here, it says you can interchange the two sides of the equation. I don't think, in this example, you need to do that. But if for some reason, I guess if we were given the opposite equation, instead of the 4 minus 2x plus 3 equals 0, what if 0 was on the left side and then everything else was on the right side? Then we would solve the same, or use the same steps, boom, boom, boom. And then in the end, we'd end up with positive 1/2 equals x. So that's usually not how you see it. They're saying, okay, you can switch whatever's on the right side of the equation, you can write it on the left and vice versa. Because usually the variable should be on the left. I guess that one I would say is optional. If necessary, yeah. If your variable ends up on the right side, you probably want to move it to the left side and switch the number, blah, blah, blah. Yeah, so let's see that. Now here's another example, maybe a little simpler looking because there's no parentheses. So in this case, I would say step 1, the steps above, I was supposed to get rid of any parentheses or grouping symbols, and then also combine like terms. I cannot combine these like terms. 5 and 29 they're technically like terms, but they're not on the same side of the equation. You got to think of like there's like a barrier here. They can't combine. I can't add them or subtract them. So it's kind of like step one is already done. There's no like terms that are on the same side of the equation. There's nothing I can really do. Now we need to do the second step, which was get rid of anything that's adding or subtracting with x, not the multiplying, and just whatever sign it had, in this case, a positive, I'll do the opposite and do a negative or subtract to get rid of it, because 5 and negative 5 add up to 0. He's all gone. 4x is now by himself. Now I'll combine these guys. 29 take away 5 is 24. Okay, now I'll divide both sides by 4. All right, that looks good. X is 6. Is that true? Yes. And I think I forgot to write, that was step 3, was to divide both sides by 4. And then step 4, we didn't need to do, I'll say check, because we didn't need to interchange both sides of the equation. But you could check the answer. That's probably a good idea, especially on a midterm. If this, the stakes are kind of high. You don't want to lose points for silly mistakes. And yeah. Or for more complicated equations too. But if you feel comfortable and you don't feel like worried that you're going to make a mistake, then it's probably fine. So, okay, let's see. I'm going to multiply these two together. 4 times 6 is 24 plus 5 is 29. That's true, right? 24 plus 25 is 29. Yes, that's a true statement. Check. So that means x equals 6 must be the solution. Yeah, notice that's something I kind of want to point out. This equation that was given to us, 29, it only has one variable. Unlike the equations in the previous section, I think we saw, like, for example, y equals absolute value x plus 1. This had infinite solutions. And this only has one solution. But the big difference is because the one on the left, this guy, has one variable. This one on the right has two variables, an x and a y. So kind of keep that in mind. I think if I were a student and I wasn't too familiar with this stuff, right now I'd be wondering, wait, why did we just get one solution? That's the only solution to this equation? I thought we had an infinite solution, according to the previous section. But yeah, that was, if this equation had a y in it as well as an x, then I would have infinite solutions. So anyway, that's the difference, in case you were wondering. I think I would be wondering that. All right, now we're gonna solve a linear equation. I feel like we already did that. Oh, okay. This is never mind. This is if it's more complicated. This is like if there are variable terms on both sides of the equation. This is kind of the complicated equations to solve. If there are variable terms on both sides of the equation, then it feels like we already did this stuff in like the P chapter, the prerequisite chapter, but maybe not. So first, if it's a more complicated equation and you want to, kind of bring all the x terms together, if you have x on both sides, first simplify any algebraic expressions on either side by removing grouping symbols if they're there, and then combining like terms if, like it says, if necessary. Sometimes it's not necessary to do that. Maybe there are no grouping terms, or there are no like terms on each side. And then if whether you do it or not, then the next step would be collect all the variable terms on one side and all the numbers or constant terms on the other side. And then the third step would be, we'll do an example. The third step is isolate the variable and solve. And then we'll check the proposed solution in the original equation. I think obviously the more complicated the equation is, the more likely I am to want to, solve, or to, what's it called? To check my answer, because I'm not super confident. It looks like there is no example for some reason, so I'm just going to make one up. The good thing is you could probably just make up whatever you want and it's all good. How about if I had like 2 times 4 minus x plus 3 equals 5x minus 7? Sure, let's solve that guy. He looks cute. How about first step, simplify algebraic expressions on each side by removing grouping symbols, blah, blah, blah. All right. Let's go for it. I do see on the left side, there are some grouping symbols. Oops, let's see if that comes back. There we go. distribute this 2. That's kind of the reasoning behind that, the parentheses being there. But if I distribute the 2, they don't need to be there anymore. 2 times 4 is 8. 2 times negative x is negative 2x. Then I'm bringing down this 3. And then on the right side, if there were like terms to be combined or grouping symbols to get rid of, I would do that. But there's nothing like that. And I just, yeah, if you don't feel comfortable with this stuff, I would kind of draw this barrier, because you might see, you know, this 3 and this 7 or negative 7 and say, I want to combine them. They're like terms, but they're not on the same side of the equation. There's a barrier between them until I move something over. And I guess at this point, technically, I'm still on step 1, because I did remove the grouping symbols, but there are some like terms here, the 8 and the 3. They're on the same side of the equation, so they're free to combine into one item. 8 and 3, they're both positive, so they'll add up to 11. And then I'll bring down this minus 2x, because he has no like terms on that side of the equation. Okay, now I'm going to try to do step 2, which is to try to isolate the variable terms on one side and the constant terms on the other side. It doesn't really matter what side you bring the variable terms to, but I think if there's too much freedom, I freak out. Like, oh, you can actually do it any way you want. I say, oh no, just give me one way. So to be honest with you, I always usually just bring all the x terms to the left side. So in my mind, this 5x is on the wrong side, and then the constant terms to the right side. This 11 in my mind is on the wrong side. But you could bring the 2x to the right and the 7 to the left, you know, as long as the constants are together on one side. But yeah, I think in my experience, I think students, and myself included, feel more comfortable if there's just one way you always do these processes. Too much freedom in math feels weird. It's like, isn't math, there's only one right way to do everything? I don't know. So, okay, I kind of want, yeah, the yellow, I'm going to highlight in yellow the variable terms. I'm going to try to get the variable terms together on this side, and then the constant terms, as they call them, or just the terms that have no x attached or variable attached. I would like them to be on the right side. But you could have done it the opposite way. It would give you the right answer, and no big deal, just whatever you're more comfortable with. So kind of similarly, I need to do that in the same way that I moved things over before. I have this 5x on the right side, but I want it to be on the left side. I just look at its sign. 5x is positive right there. If it has no visible plus or minus, it's just a positive. So I'll do the opposite. I'm going to move it over by subtracting it from both sides. There we go. That way 5x minus 5x, it's 0, so it disappears. Let's see. Maybe I'll write, and you can feel free to skip steps. I'm kind of writing a lot in one thing. You could do a lot of things in one. Oh wait, subtract. Sorry, I subtracted the 5x over. And feel free to combine those like terms right now. You don't have to write this out. But this is if you really, you know, it's been a while since you've seen math, or you have never felt good about math, then it's kind of nice to take it slow. So I've brought the constant terms together, but I have not yet brought the what do you call it? I brought the variable terms together, but I need to bring the constant terms together now. This 11 here on the left side, I've mentioned I want to bring it to the right side. It's a positive 11. To move it, I'll do the opposite and subtract it. There we go. 11 and negative 11 add up to 0. So they're gone. And then here I can actually combine these like terms. I have negative 2x minus 5x. And like we saw in the prerequisite chapter, the x isn't going to change. I'm not going to change his power. It's just the coefficients that are changing. Negative 2 and negative 5 make negative 7 together. And then on the right side, I might as well combine those in one fell swoop. I've got negative 7 minus 11 would be negative 18. All right, last thing to do is just get rid of that coefficient. It's a negative 7 multiplying by x. So to get rid of it, I'll do the opposite and divide both sides by negative 7. And I think we've got our answer. It's a negative divided by a negative, so it's a positive. But 18 over 7 isn't a whole number, and it doesn't reduce, so I think I'm just going to leave it that way. And for sure in math, algebra, and pre-calculus and on, we definitely prefer fractions over decimals, I would say, because this, if you leave it as a fraction, that's an exact answer. It's not rounded, it's exactly right. But a lot of times you put it in a calculator and you're going to have to round it, and now the answer is not exact. It's an approximation, which in real life, if you were solving this to tell someone a real life answer, then that would be fine. But in math, we like exact answers, unless there's a real life situation, I guess. All right, so that's kind of the more complicated type of linear equations you could have. And this example down here, example 3, it's talking about solving an equation involving fractions. So if you have this, it looks scary, and it would be complicated if you didn't know the kind of easier way to do it. But what we want to do is, let's see, if I'm going to write a little note here. If you have fractions, especially plural, like more than one fraction, or even one is fine, in your equations, multiply the entire equation by the least common denominator of all denominators. And then we'll see a lot of things cancel. I think we kind of saw something like that in the prerequisite, one of the prerequisite sections with the rational expressions. The very last example we did was complex fractions. And it seemed like magic. We multiplied everything top and bottom by the least common denominator of all the little denominators. And then magically all the denominators disappeared. That's going to be the same thing here. We got, okay, a denominator of 4, which is 2 multiplied by 2. We got a denominator of 14, which is 2 multiplied by 7. And then we have a denominator of 7, which is already a prime number. The least common denominator, kind of as we spelled it out before, would be, I need each prime that I see, a 2 and a 7. What's the most number of times I see a 2? This one actually has 2 of them, so I need 2 in my answer. I get to be greedy, but otherwise the 7, I only see 1 7 in each factorization. You don't see any 7 times 7, so I need 2 squared times 7, which is 4 times 7, or 28. That would be my common denominator. So I'm going to go ahead and take 28 and multiply it on both sides of the equation. And that seems like, I don't know, it seems like, can I do that? You can do anything you want to an equation as long as you do it to both sides. That's the key. You can't just do it to one term. You can't just say, I kind of want to just multiply this first fraction by something. That's against the rules. You could do it as long as you do it to every fraction. You don't want to let anybody feel left out. That would be sad, right? If you just multiply some terms by it and others no, then they'll feel so, oh, what about me? Am I not special? Every term's special. Okay, don't be sad. But I think kind of like with that complex fraction example in one of the prerequisite sections, I have to do this every time because I will make a mistake. I'm going to rewrite all 3 of the fractions or all 3 of the terms, but I'm going to leave a little space on the left side. It helps me because I'm going to write that 28 on the left, and then I can see. I don't know. What I'm thinking is if I start reducing right now, like here I say, oh, this 4 can reduce with the 28 to leave 7. Yeah, that's true for this term. But then the reducing will be different for the second term, like the 14. So I can't really reduce when it's looking like that because yeah, this 28 will reduce differently for each of these fractions. So I'm just going to show that it's next to each one. That 28 was distributed onto each of all the terms. And then just to make the reducing a lot more clear, I'm going to put the 28 over 1 because anytime you have a fraction, you're free to make it over 1. Or sorry, anytime you have a whole number. And now I feel more comfortable reducing. 4 goes into 28 7 times. So this term will just become 7 multiplied by x minus 3. Maybe I'll just keep it the same color. Why is math so much more fun when we have color? It's just me. I like looking at it. I don't mind looking back at this later if I see a bunch of color. If it's all like gray or, pencil color, boring. Let's see. Now, how about 14 can go into 28 2 times, right? 14 times 2. Yeah, so then all that's left is that 2 times the 5. That's easy peasy. You can write 2 times 5 or just go ahead and multiply it in your head. That's 10. Okay. And then what do I got going on? The next term, I've got to be careful because there's a subtraction sign. I'm going to carry him down. And then the 28 can reduce with that 7 in the denominator a little bit. 7 goes into 28 4 times. So I've got 4 times x plus 5. 4, oh, I'm going to leave that one. 4 times, and then yeah, the x plus 5, I'll put it in parentheses because the 4 is supposed to be multiplied by the entirety of that numerator. There we go. And that's a much easier equation. If you look back, I know it's like, I butchered it because you can't even see the original equation anymore. But it had a bunch of fractions and it was scary. Oh my gosh, how am I going to solve this thing? But that's equivalent to solving this. Solving the top equation and this equation, they have the same solutions. And that's as long as I didn't make mistakes in what I just did with all the least common denominator stuff. Phew, now I can solve it like they mentioned with all the steps. Okay, I'm going to distribute the 7, boom, boom. Distribute the -4. Remember, it's not just a 4, but a negative. Okay, not just a 4, but a -4, I should say. Now 7 times x would be 7x. 7 times -3 is -21. Then I've got a 10. He's waiting to see what happens with everybody else. A -4 multiplied by an x is a -4x. And then a -4 multiplied by 5 is -20. There we go. Okay. Now I can combine like terms. What do we got here? I can, let's see. Really, before I move anything to one side or the other, I'm going to move that, or combine those, the 10 and the 20. I hope you don't mind. I move everything down because we have another slide. I think, wait, no, we don't. Never mind. I'm losing it. Okay, I'm losing it. 7x minus 21 equals, okay, the 10 and the -20 add up to -10. And then minus 4x. Okay, now we can start moving things like move this to the right side, move this to the left side, et cetera, et cetera. But like I mentioned, I always just move all the x's to the left and the constants to the right. I haven't run into any problems with that so far in my life, so I think I'm okay. So here's some constant terms. I don't have an x attached, so the kind of bluish turquoise color, those are the constants. I'm going to move them to the right side. Yeah, and then the x terms or the variable terms, I'll move them to the left side. Okay. That's where they're going. There we go. And this time, maybe since hopefully we feel a little more comfortable with it, I'm going to move everything at once. So thinking about it, okay, I said I want my variable terms on the left. That means the 7x, he's already good. He can stay where he is. I'm going to just kind of copy him down, 7x. You are already on the right side of correct side of the equation. Good job, dude. And same thing with this -10. I said I want all my constants on the right side, so that he's already good. It's the other two terms I need to move. You are good. You are good. So it doesn't really matter what order, but I know I want this this variable term it's -4x. I want to move him over. The opposite of subtracting, which is what we have, is adding. So I'm going to add 4x to both sides, add 4x. There we go. That way the -4x and the 4x add up to nothing. And then what else? I want to move this 21 over to the right side. The 21 is negative, but I'm going to make it positive to cancel it out. Add 21 to both sides. Okay. And feel free, you don't have to even write this step out. You can just kind of combine the 7x and the 4x in your head and write it down, and then combine the -10 and the 21 in your head. Yeah, no big deal. Okay, but I'm going to just kind of take my time, just in case this is kind of new for anybody. 7x and 4x together make 11x equals, and now I've got -10 and 21. Look at that. Are you kidding me? 11? That's a crazy coincidence. Now I'm going to divide both sides by 11 because I want to have just x equals. I don't want to see 11x equals. And the 11 is being multiplied by the x. So I do the opposite to both sides to solve it. Well, that works out pretty good. Look at that. I got 11 over 11 is 1. So I just got x. And again, 11 over 11 is 1. Woo! Nice. Now checking is going to be tough. I need to replace all x's in the original equation with 1 and see if it's a true statement. I already forgot what the equation was. X minus 3 over 4. Okay, I'm going to have to write that down. X, oh, my bad. X minus 3 over 4 equals something. What was it? Don't tell me. 5 over 14 minus x plus 5 over 7. 5 over 14 minus x plus 5 over 7. That's sad that I just saw it and I already forgot to make sure. Yeah, don't get old, you guys. That's what happens when you get old. Walk in a room and say, why did I walk in here again? Let's see. Okay. So far, so good. Now I want to take all the x's and replace them with 1. So this is going to become a 1. This is going to become a 1. But I think those are the only x's in the equation. So otherwise, it's the same. I'm going to rewrite it exactly the same, but I'm going to wait on the x because I know I'm replacing him. Blah, 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 blah. So, okay. The x's were x's, but now they're going to be 1s. You're going to be a 1, and you're going to be a 1, and we're going to see if this is a true statement. If it's true, then I did everything right. If it's false, then I probably did something wrong. And there were so many steps in this problem. I feel like doing something wrong is very easy to do. All right. So how about now in the numerator, I've got 1 take away 3, or 1 subtract 3 is -2 over 4. All right. Is that equal to 5/14 is it's just a fraction. There's nothing I can really do yet. But now about this numerator, 1 plus 5 is 4. 4, 6. Oh my gosh. I can't add. You think that's a problem when you're a math teacher? Nah, not a problem. All right, now I might have to do a little bit of math to check to see if this is true. And I ran out of room, so I'm going to move it up here. I'm going to just rewrite it exactly the same so I have it in front of me on this side over here. All right. I want to see, I guess I can kind of do something to the left and do something to the right. The left fraction can be reduced. 2 goes into 2 once, 2 goes into 4 twice. So that guy can become -1/2. So I know what the left side looks like. If these two fractions add up or subtract to make -1/2, then we're good and I got the right x value. But if they don't combine to make -1/2, I did something wrong. But in order to combine them, I have to find a least common denominator. Between 14 and 7, I think 14 would be the common denominator. The left fraction already has that denominator, so no need to do anything to it. I'm going to keep it 5/14. But the fraction on the right, I need to transform it so it has that denominator of 14. And to do so, I need to multiply top and bottom by 2. So I got 6 times 2 in the numerator, that's 12. Okay, let's see here. Now I can subtract 5 take away 12 is -7, right? Yeah. And that reduces, okay, 7 goes into both of those, numerator and denominator. 7 goes into 7 once, 7 goes into 14 twice. Look at that. I think it's the same number on both sides. -1/2 equals -1/2. Check. All right. That means that our solution that we got, we must have done it right. It was x equals 1. But I almost think in this problem, you're almost more likely to do this, get the right answer, but then I'd make a silly mistake in here. My check would be wrong. And then I think I did something wrong in the finding x when it really was checking it that I did something wrong. Oh, geez. All right, so here, something to point out. Solving rational equations. When we solved the equation, okay, we just solved this guy, blah, blah, blah. We were solving a linear equation with constants in the denominators. A rational equation includes at least one variable in the denominator. So yeah, remember that section from the prerequisite chapter not too long ago? We were solving equations, or we were doing stuff with rational expressions, and it seemed like this looks very similar to those, but like they said, this doesn't really fit the bill because all the denominators here are just numbers. They don't have an x involved. So that's the difference. It gets a lot more complicated when you see x in the denominator. We have to treat those kind of special, but technically this is linear, and it was because I was able to multiply the whole thing by the LCD and get a linear equation. That's what we did initially. Felt like a long time ago, so I forgot I even did that. But I took the whole equation, multiplied it by 28, which is just a whole number, and then I got this equation, which is linear. You just solve for x the old-fashioned way. No need to factor or any weird stuff like that. Okay. Now this is more notice that here they're saying solve a rational equation. They didn't say solve a linear equation. That's because we see x in the denominator. X is in the denominator. Okay, but we're still going to kind of go about it the same way. Instead of multiplying by a least common denominator that is a whole number, we're going to multiply by a least common denominator that's some kind of rational or some kind of expression involving x. We've got 3 denominators here, 2x, and that's not much I can do with that. 2 is already a prime number. 18, though, I can probably write that as, what's that? 2 times 9, and 9 is 3 times 3. So that looks good, and then I've got 3x. Those are our 3 denominators, and I want to find the least common denominator. So I would need everything I see. I see a 2, I see a 3 or more than 1 3, and I see x is involved. Between these 3 denominators I've circled. How many 2s do I see? Everybody only has 1 2, or the last guy has no 2s. Well, I can only take 1. I can't take more than I see. As far as 3s go, this second denominator has 2 3s, so I can be greedy and take 2. As far as x's go, I only see 1. At the most, I see 1 in each one. So that would be what I want. There's my LCD. 2 times 3 times 3 times x, which is 18x. So, but feel free, if you can already look at this equation and know that the common denominator is 18, then you don't have to worry about that. Let's see, now I'm going to take that, kind of like we did in the previous problem, and I'm going to multiply everybody by it, 18x. So the last time it was just a whole number of 28. Now I have to involve an x. So it seems a little scarier, but I would go about it the exact same way. That's the LCD of all 3 denominators. Okay. But like we did before, it helps me a lot, and I feel like I've stayed away from making a lot of mistakes in my life for these problems just by doing this, where I'm going to write that common denominator next to each fraction so I don't mess up the reducing. Because each fraction is going to reduce differently with that 18x. I don't want to mess it up. So I'm going to just write, kind of distribute 18x goes to this first fraction, it goes to the second one, it goes to the third. 18, oh, I forgot the x, come on. 18x, 18x, you get 18x, and you get 18x. It's kind of cute. And then similarly, you don't have to do this if you feel good about it, but I'm going to put each of those 18x's over 1 and then reduce. Okay, along the diagonal, for sure, the x cancels on the leftmost fraction, but also the 2 goes into 18 9 times. So I'm really, the x is gone. All the x's are gone. I'm just left with 9 times 5, which is 45. All right, so far it's looking a lot more simple than it did before. All right, how about the second fraction, the one that's directly to the right of the, what's it called, the equal sign. Why couldn't I think of the word equal sign? 18 can just cancel with 18 outright, but the x is still there. It'll be x multiplied by 17 left over there. X multiplied, okay. I can write x 17 or 17x, that sounds more nice. And if your denominator, if there's still a denominator left other than 1, that probably means your least common denominator wasn't right. It might have been too small. All right, so now I'm going to do the last equation, or the last fraction. What's going to reduce? The x will cancel with the x, and the 3 will go into 18 6 times. So really just left with a minus sign. I can't forget there's a minus sign there. Minus, that's you, buddy. Come back. Come on down. Cute little minus. And that's a 6 times 1. That's easy peasy. I got that. Minus 6. I don't know why I wrote that 6 in blue when everything else was green. But if you're colorblind, disregard that. Don't worry about it. And okay. Now we're, oh my gosh, look at that. That makes me so happy when I see that. That equation is so much easier to solve than that. The solution to this is the same as the solution to this. So why would I make my life harder by solving this guy? When this guy is so much nicer. Yay. Took a little work to get there, but I think it's worth it for sure. All right, what do we need to do to solve that? I know I put a box around it like we're done, but we're not. I need to isolate x. The first step that we went over was I want to kind of get rid of any grouping symbols like parentheses or anything. There are none like that. And there are no like terms on the same side of the equation. So I move on to the next step. This is where I want to get all the constant terms on one side and the x terms on the other. But in this case, since there's only one x term and he's already on the right side, it feels kind of silly to move him to the left side. It's like, well, he was already there. Might as well just move the constants to the left. And since the 6 is negative, I'm going to add it to the other side to combine or to move it. 45 and 6 is 51. Is that true? Okay, equals, and now the 17x is all by himself on the right side. Only one more step. Maybe I'm going to get rid of this here. It's kind of taking up a lot of room. Blah, 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 blah. Maybe I'll just write it here. 18x with the LCD. That was the result. Okay. Now to get rid of the 17, which is what I want, because I want to see x equals in the end. What is x? So, and since 17 is being multiplied by x, I'll do the opposite and divide by it. 51 divided by 17, is that 3? That almost seems too good to be true. Is 17 times 3? Oops, 1. It is 51. That worked out pretty good. They designed these to come, usually, not always, but for the most part, you get a whole number or something, or a negative whole number in the end. Beautiful. And I could check. Didn't tell us to check, but I could. What was that? The original one. 5 over 2x equals 17/18 minus 1 over 3x. I should check. This is like one of those things you don't want to do, but you should. I don't really want to floss my teeth every night. Oh my God, it's so boring. But I guess I should. So I'm going to replace the x's with 3 and everything else stays the same. Let's see. I'm going to zoom in here so I can see it better. Boom, boom, boom. It was 5 over 2 times x, but I'm replacing x with 3 equals 17 over 18, subtract or minus 1 over 3 times x, but x is 3. Well, let's see. The leftmost fraction becomes 5/6 because 2 times 3 is 6, equals 17 over 18, subtract 1 over 3 times 3 is 9. This looks very similar to the last one. I need to, in order to tell if the left side is equal to the right side, I need to find a common denominator on the right side. It looks like between 18 and 9, I think 18 is the common denominator, and I can get there by multiplying the right fraction by 2 over 2. So I've got 5/6 equals 17/18. Take away 2/18. And what is that? 17/18 take away 2/18 is 15/18. That's hard to say. But that reduces because 3 goes into both of those, right? I can take 15 divided by 3, 18 divided by 3. I think I get 5, 6, just like the left side. So that 5, 6 that was on the left is equal to this 5, 6. Look at that. We did it right. X must be 3. That must be the right one. Yay, we did it. Woohoo. Don't get too excited, okay, you guys? I can't even see you right now, but I'm sure you are not excited. Let's see, what do we got now? Solving a rational equation. Oh, wait, we already did this. Is this the same one? They're giving us extra room. That's so thoughtful. We didn't really need it, but that's fine. Next example, solving a rational equation to determine when two equations are equal. Ooh, I like that. Wait, this is the same one, right? Yeah, okay, just making sure. Yeah. Why does it go from example 4 to example 6? I don't know. Don't worry about it. Math, you know? Let's see. This one is, the phrasing of this one's kind of complicated. Find all values of x for which y1 equals y2. What the heck are they talking about? I think they're just trying to say, find all values of x for which this left side of the equation is equal to the right side. But this y1 and y2, it's like they're just complicating stuff. Yeah. You see, they're saying, yeah, where y1 is the left side and y2 is the right side. Why even say that? Why? You're just like, I almost understood what was going on until you said that. And now I really don't understand. Thanks, guys. Okay. Anyway. So I just kind of ignore that second part. I'm just gonna focus on this thing. So the same idea. This is much more complicated. It's got x squared minus 16. So I want to do the same thing though. It's like example 4. Like example 4. I need to find the least common denominator of all the denominators and multiply every term on both sides by it. Every term on both sides by it. This the exact same steps, but finding the LCD is going to be more complicated. So if you remember from that prerequisite section, I have to factor all the denominators if necessary. The very leftmost fraction or rational expression, 1 over x plus 4. If I look at x plus 4, there's not much I can do with that. It's not factorable, it's prime. And same thing with x minus 4. It's like, that's kind of as simple as it gets, equals 22 over, but this denominator is a difference of squares. It actually factors into, conveniently, x plus 4, x minus 4, very convenient, difference of squares, okay. So it looks like between these three denominators, your LCD, you're just going to be greedy and say, I want to take every factor I see. Between the three denominators, all I see is an x plus 4 factor and an x minus 4 factor. And I look at their powers, there's only one x minus 4 for the left fraction. The middle fraction only has one x minus 4. And then the very right fraction has one of each. I don't see more than one. None of these denominators have more than one factor of x plus 4. Same thing for x minus 4. So I don't need more than one of each of them. I just need each, yeah. So I'm going to take that LCD. It sounds crazy, but I'm going to multiply both sides, or multiply the whole equation by it. All right, it sounds crazy, but a lot of things are going to cancel. So the LCD was, wait, can I move this thing? Yeah, there we go. X, doesn't matter what order they're in too. I'm writing x plus 4 on the left, x minus 4 on the right. If you do it the other way, it doesn't matter. I'm going to multiply the whole thing by it, and magical things will happen. All the denominators will disappear. The equation will be so pretty with no denominators, and it's almost going to seem like witchcraft. That can't be real. How can you do that? All right, but feel free to skip this kind of step because I'm maybe super paranoid. But like I did before in the last couple of examples, I always rewrite it again with a lot of room on the left side. And I give each fraction, or I should say each term, their own LCD. And then I can kind of see individually how things cancel. So that whole, what I wrote in orange, this LCD, I'm going to write him next to, what the heck? I'm going to write him next to everything. There we go, this guy. X plus 4, x minus 4, you get an x plus 4, x minus 4. You get an x plus 4 minus, or x minus 4. And you get one too, you silly guy. There we go. Put it over 1, just so I feel like I can actually cancel along the diagonal. Let's see, okay. I'm gonna go wild. This is the funnest part though. I'll go wild with canceling. Get to slash prices everywhere. X plus 4 cancels along that diagonal. So who's left? The x minus 4 times 1. But, you know, 1 times anything is just that thing. So I'm just going to bring that x minus 4 down. That's pretty nice. So far, it's looking good. The left side is just x minus 4. I like that. How about the next fraction? Oh, wait, why'd I put a plus? Or why'd I put a equals? It's a plus. Is it sad? Like, I can do math. I can do a lot of math, but just copying my own writing, I can't do that. The plus all of a sudden became an equals for no reason. Just because life is boring and I want to make it more interesting with chaos. All right, the next fraction I got x minus 4 cancels along the diagonal. All right, who's left? Just your x plus 4 times 1, but similarly, x plus 4 times 1 is just x plus 4. And then if you want, you could leave these in parentheses. I kind of, in this case, it doesn't matter. I should, though, because if this was a minus, oops, instead of a plus that I circled here, if this was a minus, I would need to distribute that minus. So I probably should leave these in parentheses just to be safe. Because next time it could matter. Equals, and this is my favorite one. Look at this. What's going to cancel with this fraction on the right side? X plus 4, cancel. X minus 4, cancel. Who's left? Just 22 all by his little lonesome. Isn't that awesome? So much better. This equation is so much better. Yeah, and now, yeah, if there was something to distribute, I would do that, but there's not really any reason that those parentheses are there, so I'm just going to remove them. Same thing here, I can distribute a plus, but it doesn't change anything. The x was positive, it stays positive. The force was positive, stays positive. Oh my gosh, this is beautiful. It almost seems too good to be true. This is where I would, if as a student, I would second guess my work. There's no way this is the right answer. It's too easy. An x and an x makes 2x. A negative 4 and a 4 actually add up to 0. So they're kind of like nothing left there. I can just move the equals 22 over. Look at that. One more step. To get x by itself, I just need to divide both sides by 2. God, that's so beautiful. What a beautiful, beautiful thing. Most people wouldn't describe any math as beautiful, but hey. X equals, what's 22 divided by 2? 11. Down, 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 down. Sometimes after all that, like a complicated problem, I was just so kind of very focused on each step I was doing. I even forgot what was I doing and why did I get, what was 11 again? 11 is what? The answer to what? Oh yeah, that's right. It was this equation here. What? So apparently there's only one solution to this equation because they said find any, what they say? Find any values that'll make this equation equal. Sometimes you might get more than one solution, and we'll probably see that in the future, but in this case, there's only one solution to that cute little equation. Should we check it? I don't really want to. Should we? All right, I'm gonna do it just because I'm supposed to. But you can feel free to skip this part of the video. I would not blame you, and I wouldn't know if you did or didn't anyway. All right, I'm gonna do it. Check my answer. I think x is 11, supposedly. So I'm gonna replace it wherever there was an x. Okay. I'm just gonna rewrite this exact equation. Oops, I was just about to say with no x's, and then here I go writing an x. Get rid of the x, get rid of the x, but where the x was, I'm gonna put a 11. 11, 11, 11. Okay, kind of individually simplify each fraction and see if it's true. On the very left fraction, it's 1 over 11 plus 4 is 15. And then on the second fraction, 1 over 11 minus 4 is 7 equals, okay, 22 over 11 squared. 11 times 11 is 121. Take away 16 is, ew, what is that? 105? Wait, is that true? I think so. Sure, whatever. Ugh, that's not pretty. I want to see if that's true. I need to find a common denominator. Ew, between 15 and 7, it would be, this needs to be multiplied by 7, and this needs to be multiplied by 15. Yeah, sometimes if they, like 15 and 7 have nothing in common. If there are no primes in common or no variables in common, it's just like basically multiply them by each other, top and bottom. So this becomes 7 over, what even is that? 105? Look at that. Interesting that happens to be the same denominator over here. And then plus 1 times 15 is 15 over 7 times 15. We just did that, 105. Is that true? Oh, I think it is, because look at these numerators add up to 22. So it really says 22 over 105 equals 22 over 105. I don't really know what 22 over 105 is, but that's true. That something equals itself. Boom. Man, we're good. As a team, we are good, my friends. This is good. This is fun. Let's do this every day. Types of equations. Identity, conditional, inconsistent. All right, kind of getting back to some terminology here. If we're on a midterm or final. I'm not going to ask you about this terminology. Like, oh, here, problem 1, define what a conditional equation is. You know, you won't really need to worry about it. It's more just like if that's said out loud during a video, then you'll know what I'm talking about. I guess it's more, yeah, more like here, we'll spell it out so that you'll understand what words we're saying, but you don't need this too often. An equation that is true for at least one number is called a conditional equation. The examples that we have worked so far have been conditional equations because there's only 1 or 2 solutions maybe. And which sounds crazy. It's like, well, how many solutions were you expecting besides 1 or 2? Well, below we'll see the opposite of that. And an equation that is true for all real numbers is called an identity. And that sounds crazy. How can there be an equation that's true for every single number? Well, later in this section, we'll see an example of that. An equation that is not true for any real number is called an inconsistent equation. Probably just, yeah, I think we probably don't need to write an example of the first one because like they said, all the examples so far in the section have been that way. But something like this one, an equation that is true for all real numbers is called an identity. Like what if I said, let's see, x equals x. There's my equation. It's very simple, but of course it fits the bill because that's true for any x value. If you replace x with any value, that's going to be true, right? X equals x. Of course, x equals x for every x value. There's more complicated ones, but it's usually something like that to where the left side and the right side are exactly the same thing. Sometimes in disguise, because I could say, for example, 2x plus 6 equals 2 times x plus 3. Those look different, but if I were to distribute this 2 in, I would get the same thing. It would be 2x plus 6 equals 2x plus 6, which is obviously true for every single x value because they're exactly the same on the left and the right. Of course, that's always true. You don't have to even specify what x is. Of course, that's going to be true. But an inconsistent equation would be like, it's actually harder to find. Let's see, like x plus 1 equals x plus 2. That can never happen. And if you were to try to solve it, x would just disappear, right? If I imagine subtracting the x over to the left side, the x's would just disappear. That one's not as obvious, but it kind of makes sense when you reason it out. How can you take a number x and add 1 to it and have it be the same as if you take that same number and add 2 to it? You know, that doesn't make sense. How can you add 1 and then add 2 separately and have them be the same thing? Anyway, we'll see some examples of that over here. Let's see. So here they want us to solve these equations and then tell what kind it is. I don't want to give it away. I'm going to hide the answer. Oops. The answer's down there. Pretend you don't see that. Solve the equation. Okay, what do we got here? Let's solve it as if we don't know anything weird's going to happen. Oh, okay, let's see what it is. First thing we're supposed to do is kind of distribute, get rid of any grouping symbols and yada, yada. Okay, I'm going to just rewrite the left side because there is no grouping symbols I need to worry about and there's no like terms. But on the right side, I need to distribute that 4. It'll be 4x minus 4 and then plus 3 that was already there. These are like terms. Those are going to be combined now. 4x, then I've got minus 4 plus 3 makes minus 1. And I think this is very similar to that last example I just wrote. It looks like the left side and the right side are almost the same, except the constant term's wrong. But pretend like I don't know that. I'm gonna move this 4x to the left side and this 7 to the right side. Okay. Because like I said, I always just move the constant terms to the right and the variables to the left. So these two will be combined. All my variable terms are together. And then all my constant terms are together over here. Let's see. But the left side, 0 or 4x minus 4x is 0. And then on the right side, I've got negative 1 plus 7. That's 6. This is a statement that says 0 is equal to 6. That's never true. I'm no math teacher, but I'm pretty sure 0 is not equal to 6 ever. So as I said, this is a false statement. That means that this equation is an example of an inconsistent equation. That means they gave us this equation there that didn't have a solution at all. Yeah, similar to that last one we wrote up there. Now, how about this one? Let's do something similar. Let's see, see if this is inconsistent, an identity, or a consistent system. Consistent, inconsistent, I think I'm spelling this right, or identity. Because like we said, consistent, that's like a finite number of solutions, but at least one. I guess technically 0 solutions is finite. Solutions, at least one. So you gotta have one or more solutions. Inconsistent is no solution. like we saw before. Identity is all numbers are solutions. Solutions. Yeah, like we said, the first one, x equals x. That's true for every single x value you can think of. Of course, x is equal to x. I don't care what x you say, you know, it's always going to be true. There, okay. Let's see what this one is, this equation. And sometimes it's hard to tell, they disguise it. They're hiding all the interesting things that are going on in here. So, okay, there's the same kind of thing. If I see some grouping symbols or like terms, I'm going to combine those or group them or whatever. The left side of this equation, similarly to the last one, there's nothing I can really do. But now on the right side, I distribute the 9. 9 times x is 9x. 9 times 1 is 9. Then I've got this minus 2x. And before I do any moving, I'm just going to combine the like terms I see that are on the same side of the equation. 9x minus 2x, those can be combined. On the left side, I've got 7x plus 9, okay, equals 9x minus 2x is 7x. And then I've got the plus 9. He has no like terms to combine with. Now I'm seeing this is 7x plus 9 equals 7x plus 9. Yeah, that's always true. The left side and the right side are exactly the same. So I'm kind of expecting something weird to happen, but let's pretend it's not going to. Let me move this 7x to the left side to try to get the variable terms on the left. But the 7x minus 7x on the left becomes 0, nothing. And then I want to get all the constant terms on the right, so I'm going to subtract that 9 over to the right side. But then again, 9 minus 9 on the right side equals 0. 0 equals 0, that's always true. As opposed to the last example where I got 0 equals 6, which is never true. Always true, so as they said, this is a true statement, and it didn't matter what x was. I never even specified what x is or never found what x is. The solution set for this equation is the set of all real numbers, meaning x can be anything it wants. They call that equation an identity, meaning it's always true no matter what. All right, let's do one more example here, and then I think we'll, yeah, wait, it's got the, yeah, okay. This is funny. Oh man, it's not funny. This is another depressing one. Come on. Persons with a low sense of humor, so far sounds good, have higher levels of depression. Damn it, man, it's always sad. In response to negative life events, whoa, have higher levels of depression. Huh, than those with a high sense of humor. Wait, what? See, that's what you hear people like in bad situations joking, and you're like, come on, how can you joke at a time like this? That's why, because it makes you less sad or something. Here I am doing the same thing. This can be modeled by the formula capital D. Okay, what do you think that is? Depression, I guess, equals 10x over 9 plus 53 over 9. What does x represent? Okay, it represents the intensity of a negative life event. What the hell? How do you even quantify that? And D is the average level of depression in response to that event. Okay, yeah, what kind of numbers are we expecting here? Okay, if the low humor group averages a level of depression of 10, and what's that a level, is that a scale of 1 to 10, or what kind of scale is that? In response to a negative life event, what is the intensity of that event? Ooh, okay. So usually in these types of problems, they give you this equation and they're either telling you one or the other variable, and you got to go find the one you're missing. So this was our equation, blah, blah, blah. And they gave us 10. Okay, that's either X or D. Let's see what they say. If the low humor group, a level of depression, I think that was D, right? D is the average level of depression. Yep, okay, so they gave us, dang it, I was hoping they gave us X, because that would be a lot easier. But of course, no. There we go, so I need to replace this capital D with 10 and then solve for X. Replace, then solve for the variable you don't know, which of course is X for X. Man, it would have been a lot easier if they gave me X, but no, of course not. What are we gonna have here? So I've got, what is it? Oh yeah, I'm gonna put a 10 where capital D was, and I think I mentioned this in a previous section of this. Make sure, like, if you have to do something with the variables here in the homework, if you're typing this in, make sure you keep the D capital and the X lowercase. So if you type it in, don't do lowercase d equals 10, or don't accidentally do capital X because it looks like it was lowercase. It's very case sensitive, which I feel like they probably could have easily programmed the answer to have a capital or a lowercase d, but they're too, anyway, don't go there. Okay, we want to solve this guy. So the capital D was replaced with 10. All right. I think I'm just talking a lot so that I don't have to do this problem, but I guess I should. All right, let's see. I'm going to, how do we solve these again? Oh yeah, I'm gonna multiply the whole thing by the LCD. I would just try to like isolate X, but seeing fractions running around, it makes me sad. Speaking of depression, multiply both sides by the LCD. So looking at it, there's only two denominators. They're both the same, so that's got to be the common denominator. But don't forget, okay, this is where I've seen students make mistakes is it's like, I think I'm multiplying the whole thing by the LCD. The purpose is I want to get rid of the denominators, but the only way to do that and follow the rules is if I multiply every term by it. Even though that 10 on the left side doesn't necessarily need it, I don't really want to multiply 10 by 9, but I have to balance this equation out. I really like to see the 9's canceling here. I don't really care too much about this 10. But yeah, I can't just multiply the terms I want by the LCD. It has to be every single one for this equation to balance out. So really, I do have to do the 10 on the left times 9. I'll write the 9 pretty soon, like we've been doing. Da, 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 da. This guy's going to get his own 9. You're going to get your own 9, my friend. Don't worry, everyone gets their own 9. There are only 3 terms in this entire equation, but if there were more, they would all get them, all however many there are. 9 for you, 9 for you. And I'll put that, actually the very first 9, I don't need to put it over 1. There is no fraction to contend with here, but the left or the second and the third one, I probably should. All right, the left side, just 9 times 10, that's 90. I could do that. And then over here, the second fraction, 9 and 9 cancel each other. So I'm left with just 10x. And then on the very rightmost fraction, the 9's cancel, leaving that 53. All right, this looks not so bad. All right. Once the fractions are gone, I swear, I always think I must have done something wrong. It looks too nice. And this is another one where I always say I'm going to move everything to one side, like either move everything to, or I always want to move the variables to the left, but there's only one variable. He's already on the right side, and he looks like he's happy and comfortable over there. So it's easier to move that one constant term next to him to the other side. It was a positive 53. I'm going to subtract it to get rid of it. 90 take away 53 is 37. Wait, is that true? I think so. Equals 10x. All right, last step to isolate x, I just need to divide both sides by 10. Okay, looks like that's x. X is 37 over 10, which doesn't reduce. So this would be a good answer, you know, and in a math class. Like I said, you don't really want a decimal, but since this is real life, you might want to actually divide it to determine what this means. 3.7 would be the number. And this problem is kind of silly because what the heck? What is the intensity of the event? 3.7 is the intensity of this event. What the hell does that even mean? On a scale of what to what, you know? What do we say that they have persons with a low sense of humor have higher levels of depression in response to negative life events than those with a high sense of humor. This can be modeled by the formula. Okay, but X is the intensity of the life event. Okay, is that a lot? Is that a little? Compared to what? Oh my God. So I think they just gave us an example, but if this was something we cared about, we would know the scale from what to what. What's the highest level of intensity? What's the lowest level intensity? Anyway, hopefully there'll be an example someday where it's not a bummer, you know? Talking about depression, the last one, what were we talking about? Divorce rates. Jeez, oh my gosh.